Hey guys, welcome back to day 40. We're talking about calorimetry today. And specifically what we're talking about is heat transfer. We know that when two substances of different temperatures are combined, heat, which is of course thermal energy, flows from the hotter substance to the cooler one. And we know this, and this actually is a result of the second law of thermodynamics, which we talk about in Chem 2. We know hot goes to cold. Just so you know, when we put ice into a drink, the ice is not technically cooling down the drink as much as the drink is actually melting and warming up the ice. And we'll talk about that soon. When we have two substances, they both have a heat content, Q and Q. One is for the system that we're going to talk about, and the other one is for the surroundings. And they equal each other, except one is negative. Heat transfer. There's no energy lost in heat transfer. Now, how do we measure this? This is measured in a calorimeter. Calorimeter. I always pronounce it calorimeter in class because we have color meters and calorie meters. Color meters have to do with light measuring, and calorie meters have to do with heat measuring. There's two types. Bomb calorimetry occurs at constant volume and measures delta E, which is the change in internal energy for a reaction. The other one is coffee cup. And coffee cup calorimetry occurs at constant pressure and measures the heat of a reaction. Well, what does that look like? Well, here's what they look like. You have a bomb and a coffee cup. The coffee cup is just what you think of. So let's look at the coffee cup one first. You have a thermometer to measure the heat transfer, right? The temperature change. There's where we get delta T from. Both of these get a delta T. There's the thermometer delta T. The bomb also gets a delta T. The glass stir, so you can actually take the cork lid and swirl around. And you have two styrofoam cups with your solution and your, let's say if you have a hot metal and water, or if you have, you're looking how much a salt solution will decrease. Usually you're mixing two different liquids like a warm water and a cold water or something like that. The bomb is a little bit different. You have a tightly sealed bomb down here. That's your bomb in there. So all this is bomb. And that's definitely a fixed volume. And the volumes are going to change. You have oxygen in your sample in there. You ignite your sample until it burns and measure how much energy comes out. We know how much the bomb down there is going to absorb. And so all this heat goes to the water, and we get a delta T for the water, and it works out. So a lot of times in lab, we go with coffee cup because that whole expense is a lot cheaper than this expense. And for our purposes, we get good enough results in Gen Chem 1 and Gen Chem 2. Now let's talk about energy and changes of state. Changes of state. We know you can have solid ice, so I'm going to put solid here. And then we can go to a liquid. And we can go to a gas. You can go solid to a liquid and liquid to a gas. We can do that. So in the solid state, we can raise the temperature of ice, lower the temperature of ice until it's melting point. And then the melting point of water happens to be 0 degrees Celsius, and then we can melt it or freeze it. It takes energy, or energy is released when this happens. And then obviously in the liquid phase, you can warm and cool water to the boiling point. Once it's the boiling point, no longer can you keep heating it, it's going to change into a gas. And so now in chemistry land here, changes of state. Take place at constant temperature. So for example, melting ice will remain at 0 degrees Celsius until all the ice is melted. So we know that in the range from solid and in the range of liquid, in the range of gas, we have Q equals MC delta T. Right, eventually there's a temperature where almost everything would break down. But it goes from absolute 0 to the melting point, whatever that melting point would be, and then from the melting point to the boiling point, and then from after the boiling point on until it breaks down. Those are the Q equals MC delta T where we can change temperature. In the phase changes, our phase changes, right? We have energy required. So, for example, you probably all boiled water successfully. Almost everybody probably has boiled water successfully. You put it on the stove, top, turn the burner on, and let it boil. As soon as you take the water away from the burner, it stops boiling. We need constant heat going into the water. However, the temperature is not changing. Well, exactly, because it's changing at constant temperature. And so for this purposes, solid to a liquid, Q would equal the standard or the change in enthalpy or the heat, we call it the heat of fusion times the mass. And for the gas, liquid gas, Q equals delta HV for the mass. Those are your two formulas. Same formula, but delta HF is for solid to liquid, and delta HV is for liquid to gas. That's very important because they're different numbers. Okay, they're different numbers. In fact, I'll define for water. Let's talk about for water. Our constants. You have the specific heat of ice, and that is 2.1 joules per gram degree Celsius. The specific heat of liquid water, 4.184 joules per gram degree Celsius. And the specific heat of steam is 2.0 joules per gram degree Celsius. Delta HF happens to be 333 joules per gram. Delta HV happens to be 2260 joules per gram. So those are your constants for water, for H2O. Let's draw this as a heating curve. And our example will be 10.0 grams of ice at negative 10 degrees Celsius to steam at 110 degrees Celsius. So that's going to be our example. We're going to take 10 grams of ice, which is not a lot of ice, and we're going to take it from negative 10 degrees Celsius, which is possible, right? Because ice can go all the way down to probably, actually, I don't know if it goes all the way to absolute zero. I'd have to look that up. But it can go down pretty cold. I don't know if we can get the surroundings cold enough to get ice as cold to absolute zero, but it can get down negative 100 degrees Celsius, no problem. We can make that happen. All the way up to zero. Ice starts going from solid to a liquid at zero, and then at 0 to 100 is all liquid water, and then over 100 is steam. So on our heating curve, we have 5 stages, and let's draw the curve, and then we'll talk about those stages. Draw. We get our x, y, xe. Here's our heating curve. On the y-axis will be temperature in degrees Celsius. On the x-axis is heat added in joules. So obviously temperature depends on how much heat we add. So that's why temperature is on the y and heat added is on the x. We will start right here. Will be negative 10 degrees Celsius. 0 degrees Celsius. We'll have 100 degrees Celsius and 110 degrees Celsius. That's my scale, which is not, it's truncated in the middle. We start with ice. We start with ice right here. Start right there. Ice, 0 heat at negative 10. And it quickly rises up to 0. Once it's at 0, it melts. And it'll melt at 0. And then once it melts, it warms up to 100. Then once it's at 100, it boils. It's going to boil from here. Let's go to there. And then it will be a gas. Oh, wrong color. And there is my end. So we have warming ice here in purple, and that's number 1. Number 2 is melting. Number 3, step 3 here, is warming water. Number 4 is boiling or vaporization. And step 5 is heating the gas. Heating steam. That's our steps. So this is a cumulative process, as you can see. Just like shopping. If you are a weekend shopper and you go to 2, 3, 4 stores, everything you spend is cumulative. Well, I spent $20 here, I spent $40 there, spent $60 there. Well, that all adds up though to the total amount you spend. Or if you're a website shopper, same thing. Amazon and this website and that website and what other website, whatever websites you guys spend on, right? It's all additive. Like, how did I spend that much money? Well, you add a little bit, and a little bit, and a little bit equals a lot. Just like here, a little bit, little bit, little bit, little bit, little bit equals a lot. So it's cumulative. So if we look at our overall heat, Q will be equal to all of our steps, which would be warming the ice, and each Q is added, right? They're all Q equals something, right? Q equals MC delta T, or Q equals delta H times the mass. So warming ice plus melting plus warming the water plus boiling or vaporization and warming steam. So it's all cumulative. Q will equal the formula for warming ice is Q equals MC delta T. So warming ice would be M C of ice delta T of ice. So I'm using subscripts to specify what exactly we're talking about, because there's more than one specific heat and there's more than one temperature change. Melting is Q equals delta HF times the mass. So we'll use delta HF times the mass, because the mass is not changing. Whether it's a solid, whether it's a liquid, whether it's gas, doesn't change. Warming, Q equals MC delta T. So we'll use M, specific heat of water, delta T of the water. Vaporization, Q equals delta HV times the mass. So we'll just type that in here, delta HV times the mass. And then warming steam. Warming would be a Q equals MC delta T situation. We will have MC of steam. Delta T is steam. Q. Let's put our numbers in. I have 10.0 grams of ice. Specific heat of ice was 2.1 joules per gram degrees Celsius. And delta T, final minus initial. Final is 0. 0.0 degrees Celsius minus initial, negative 10 degrees Celsius. So it's 10 degrees Celsius. Plus, delta HF is 333 joules per gram times 10.0 grams plus my mass of, now it's liquid water, it's still 10.0 grams of water. It's now 4.184 joules per gram degrees Celsius, and delta T would be 100 degrees Celsius, the final, minus the initial of 0. Plus, now I'm going to come down my room, delta HV, 2260 joules per gram times our 10.0 grams. And then last but not least, our mass of now steam is still 10.0 grams. Our specific heat of steam is 2.0 joules per gram degrees Celsius. And 110 degrees Celsius minus 100 degrees Celsius. Oh, here we go. Q will equal, for melting or warming the ice, step 1, warming the ice, I get 210 joules. 210 joules. For the melting of ice, we get 3,330 joules. For the water, I get 4,108 d4 joules. Yes, 100. Yeah, 4 times 1,000. 4,000. For boiling or vaporization, I get 22600 joules, 22,600 joules. And then for the gas, I get 200 joules. Overall, for Q, is 30524 joules, or to 3 sig figs, 30.5 kilojoules. And that's the heating curve of water. So that's each step. It's all cumulative. And so now, when we look at these problems we're about to do, we got to look at what the substance, a lot of times it's going to be water, but what the substance is doing. Is it warming up? Is it cooling down? Is it melting? Is it freezing? Is it boiling? Is it condensing? And we got to use the right formula depending on where we're at. If we look at, if we're just in the solid region, we're just solid. We're in the phase change. If we're in the liquid region, we're in a phase change. And again, it just depends on where we're at. And we use the appropriate formula, because those are the formulas. There's really only two: MC delta T or delta H times the mass. Plug in the right constants. So let's do an example. I have 20.5 grams of ice at 0, and they're added to 128 grams of water at 76.5 degrees Celsius in an insulated container. We're going to calculate the final temperature. So there's what we have to do, is calculate the final temperature. We're looking for the final temperature of everything. Assuming that the specific heat of water is 4.184 joules per gram per degree Celsius, and the heat of fusion of ice is 333 joules per gram. Now there is a special word here, and this special word is insulated. What does insulated mean? Well, usually if something's insulated, it means it's going to help keep either the heat in, or the heat out, or the cool in, or the cool out. Right? You want your walls insulated in your home. You want your pipes insulated. Sometimes you have coats that are highly insulated with like Thinsulate or whatever, Gore-Tex. Well, in this case, our insulated container means it's like a cooler. There's no, if you get a really nice cooler, Yeti, Orca, there's several other ones that are out there that are really good coolers. Some of them are really expensive, some of them are less expensive, but they're really good coolers, and they'll keep ice for a few days in heat. That's what we're talking about. Now, in our chemistry land, we assume zero heat transfer, which is really nice. So we assume no heat's gained or lost. What do we have here? We have 20.5 grams of ice at 0. All right, to 128 grams of water at 76.5. If I just draw a picture here, I have liquid water in this. And it happens to be 128 grams and 76.5 degrees Celsius. We're going to throw in some ice cubes. I'm just going to draw one big ice cube. And it's 20.5 grams. And it's 0 degrees Celsius. Well, we're going to calculate the final temperature. If we're going to calculate the final temperature, I'm assuming that all the ice is going to melt. Otherwise, the final temperature would be 0. If I still have water and ice, the final temperature is 0. So I'm assuming that the final temperature is not going to be 0. We are going to find out if this assumption is valid or not when we do our calculations. So we have the ice side and the water side. They both have heat, Q and Q, and they're going to be equal to each other. Which one's losing heat? One of them's losing heat. Which one? Well, it looks like the water is going to get colder, so that means the water will be negative. That's very important, that -1, the way we're going to do it. Side note, you can keep everything positive and keep everything the absolute value, and it'll work out too. It's up to you. The ice. What's the ice physically going to do here? It's going to start melting, right? It's going to melt. Also, if it melts and the final temperature is not 0, what else does it have to do? It has to warm up. And the water is going to cool. Do I have a formula for warming, melting for ice? Delta HF times the mass. So that's the melting formula. And then we're going to warm up. MC delta T of ice. But C, what C are we using there? If the ice melted, is it still ice? No, it's now liquid water. So we're going to use the specific heat of water. That's very important. And this is going to equal, water cooling would be negative MC of water, delta T of water. Now, delta T, we're going to break down one more, let's break down one more line. So I'm going to write this down one more time. Delta HF times the mass plus M, specific heat of water, delta T of ice equals negative MC of water, delta T of the water. And it's going to be the final temperature, which what we're looking for. And the final temperature is going to be the same for both the ice and the water. We're looking for TF, the final temperature, minus the initial temperature. Well, the initial temperature of the ice is 0, because the problem said so. And the initial temperature of the water was 76.5. And that's right here in the problem. 76.5 for water, 0 for ice. Now let's plug in all of our values. Delta HF is 333 joules per gram. And we had 20.5 grams of ice plus 20.5 grams of ice, specific heat of water of 4.184 joules per gram degrees Celsius, and then TF, because TF minus 0 is just TF, equals negative 70, the mass of water was 128 grams. Right, 128 grams of water, yes. Specific heat of water, 4.184. And TF minus 76.5 degrees Celsius. And at this point, the chemistry is done. We are now doing an algebra problem, which is great news because we all can do algebra. Starting on the left, 333 times 20.5, I get 6827. 6827. And I'll use green for joules. Plus, what's this? 20.5 times 4.184 times TF. I get 85.8 joules per, the grams are gone, degrees Celsius times TF. On the right side, I have to do the 128, negative 128 times 4.184, get that number, which is 536, and then times by TF and times by negative 76.5. So I get negative 536 joules per degree Celsius times TF. Very important. There's a negative and a negative plus 40970. 40,970 joules. I'm going to get the TFs on the left-hand side, so I'm going to add 536 to both sides with TF to get TF on the left, and the joules on the right. So if I add the 536, I get 622 joules per degree Celsius times TF equals, on the right-hand side, I get 34,144 joules. Then we divide both sides by the 622 joules per degree Celsius. TF, I get 55 degrees Celsius. And that's one of the harder problems. So what do? Recap. Have ice in the water. The energy from the water is going to the ice. The ice physically melts. Then it warms up. The water just cools down. And we put our formulas in, put our constants in, and our amounts, and we solved. So this problem, we just did, where we have ice water mixing. And this problem here they're both included in this top 5 favorites. So I have top 5 favorites, as you know. So far we've done combustion analysis. We've done solution stoichiometry, where you have to write down the balanced equation from words, figure out the limiting reactant, get percent yield somehow is in there. That's the second one. This is the third one of a top 5 favorite. So we have 20 grams of steam at 100 degrees Celsius. It's bubbled into a mixture of 50 grams of water and 200 grams of ice at 0, where all the steam condenses to water. What is the composition of the system at the end? Great question. Where we do this? My recommendation is let's draw a picture. Let me draw a picture here. I have a container, and it has a port down here. In this container, we have 200 grams of ice. So there's my 200 grams of ice. And I have 100 grams of H2O, liquid water. What temperature does it have to be? Well, if I have ice and water, and it tells me it's at 0 degrees Celsius. We have some steam coming in. Well, we'll use steam coming in. We know how much steam. 20 grams, and it's 100 degrees Celsius. And it's going to bubble, 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 bubble in. All we want to know is how much ice and how much water is at the end. So if all the ice melts, then everything will be water, because the steam's going to condense to water. It's not going to freeze. So we need to know, does the ice melt or not? Well, I'm going to assume that the steam condenses and cools to 0 degrees Celsius. That's my assumption. We're going to find out if the assumption is wrong. Then we know that everything's going to be liquid water. So if we look at just the steam, it's got to condense and cool. Condensing, the formula would be delta HV times the amount, so Q, plus M, now it's specific heat of water, delta T for the steam. Q, delta HV on our constants, 2260. 2260 joules per gram. And the mass of the steam is 20 grams. And 20.0 grams. It's now liquid water once it condenses, so it's 4.184 joules per gram degrees Celsius. And delta T, I'm assuming the final is going to be 0 minus the initial 100. So it would be, technically that would be a negative 100, wouldn't it? Since we're condensing, this number is negative as well. And it's negative, well, 0 minus 100. 0 degrees Celsius minus 100 Celsius. Perfect. So if we do this, Q would be negative 53568. Joules. This is the heat released as steam condenses and cools to 0. So now we got to check the ice. Let's check the ice because we really just need to worry about the ice here. Because if we're at 0 degrees Celsius, the water's not doing anything. Ice is going to melt. How much? How much melts? Well, Q equals delta HF times the amount. We know Q. Q is 53,568 joules. And remember, the sign is just negative or positive. That means the direction. It's leaving the steam going to the ice. Just like if $20 leaves my wallet and goes to my wife's wallet. It's a negative 20 to me, positive 20 to her, and that's okay. That's just the direction of the money. It has nothing to do with the value of the money. Just like here, that's the direction of the energy, not the value. Delta H is 333 joules per gram, and we're going to look for M. So we divide for M, I get 161 grams of ice that melts. That's how much melts. What do we start with? 200. So does all the ice melt? No. No, it does not. So the amount of ice, I start with 200 grams of ice. Water, I start with 100 grams. And 20 grams of steam. 20 grams of steam is added. And we're subtracting 161 grams of ice melting. And we're adding the 161 grams of ice there. So it looks like ice, I have 39 grams of ice. And for water, we have 231 grams at the end. So we melt most of the ice, but not all of it. A little more than 3/4. So what do? We assumed, because there's amount of ice and amount of liquid water, we assume, oh, there's probably some ice left. And then we calculate how much energy can the steam release. So if the steam can release that much energy, how much can the maximum amount of energy come out of the steam? And that's what we calculated right there is 53,568 joules. Then we said, how much does that ice does that 53,568 grams or joules melt? How many grams of ice does that many joules melt? It was 161. And then we did our what melted, what didn't melt, and all that. One little small The point is, if this number, 161, was more than 200, all the ice would have melted, and everything would have just been ice. It wouldn't even it didn't ask for the final temperature. So these last two examples are probably the hardest I'm going to get you in Chem 1. That's why they're top 5 favorites. So this one and this one could be there too. Don't memorize the problem with numbers. It's the mixing of ice and water and steam, maybe all three, maybe not all three, and there's a final temperature in there, or there's an amount left. That's the type of problem that we're talking about. So that concludes day 40. Hope it worked for you. Have a great day. We'll see you next time.